So we were discussing a differential amplifier and their common mode response in the last class. So let's start off from there. So quickly, can you tell me in this structure, if I increase VI, right? So we are talking about common mode response. So common mode means both the inputs are tied together and they increase simultaneously. Input that is common. So I have applied incrementally identical voltages at the gate of M1 and M2. So can you tell me what will be the incremental current through either M1 or M2? Zero. Yeah, that's absolutely correct. And what's the reason? Right. So there is no incrementally, there is no difference between how M1 and M2 are working. So if an incremental current through M1 were to flow, it will flow from top to bottom. Similarly, if an incremental current were to flow in M2, it would have flown from top to bottom. Now, if you do a KCL at Vx, the only possible solution is that both those currents are zero because they are identical and in the same direction, right? So other way of approaching the same thing is, as you pointed out, if we do an incremental analysis with only input applied at M1 and input applied to M2 separately and use superposition, then we will see in one direction the current, in one case current is flowing from in this direction, other in the opposite direction, and they are exactly equal and opposite, and they cancel each other. Essentially, the total incremental current when the input is simultaneously applied at the gate of M1 and M2 will be zero, right? So this is fine. This we talked about in the previous lecture. Then we said that what is the root? I mean, if we don't consider the current source to be ideal, right? So in our case, it's a transistor. So since it's a transistor, so it will not be a perfect current source. You will have some output impedance, and let's call that R0. So in the presence of R0, things change, right? Because now, in the previous case, when we were doing KCL at these nodes, right? So these two currents were identical, and we are summing them up at Vx, and only possible sum was zero, right? In this case, it's not the case. In this case, the current, the total of the incremental current flowing through M1 and M2 can escape through R0. So the KCL will have a solution. Okay. So if that's the case, we can figure out, we can do an incremental analysis of this structure to find out what will be the common mode output response. And it will definitely not be zero. Okay. So now there are multiple ways of approaching this problem. One is obviously the way we have been discussing till now, that is use superposition, apply input at one side, find out whatever is the current, and apply input at the other side, find out whatever is the current, and then go ahead and sum them. Okay, so we can do that. Let's do that quickly. So let's assume that the current input voltage is only applied at Vi at M1. So what will be this current approximately? So this we have done multiple times, so you should be by heart on this time by now, kind of. So what is the input impedance? What is the impedance that this guy sees? So what is the input impedance here? 1 over GM2. So what is the impedance here looking in? 1 over GM2 parallel R0, which is approximately 1 over GM2. And let's assume GM1 and GM2 are identical. So in that case, it's basically 1 over GM. So if you see 1 over GM resistance connected at the source, which means I am talking about this structure, and this is Vi, then what is the incremental current? You can look up and tell me. Yeah, GMVI by 2, right? GMVI by 1 plus GMR, whatever is R connected. So essentially, this is GMVI by 2. Now, which current are we interested in? We are interested in this part of the current now for CMR, for common mode rejection, right? Because the other part will cancel when we go to the gate of M2 and apply the input there. So this magenta part will not get cancelled. So what will be the magenta current? This I1, let's say, this will be. So again, this is a current division between two nodes, right? What are the two nodes, the current division I'm looking at? So I am having a current. This, I should not draw it as a current source. So I have current, some current is coming in and it's seeing a resistance R0. And again, it's seeing a resistance of 1 over GM, right? This is at Vx. This is at Vx node. So I am interested in this current. Let's say this is I. So what will be the current through R0? Right. So this current will be I times 1 over GM by 1 over GM plus R0, which is essentially I by 1 plus GM R0. Right? So what is I? I is GMVI by 2. So this will be GMVI by 2, 1 plus GM R0. Right? Yes. Correct. Yeah. So his question is, while we were calculating I was neglecting this R0 here, right? Effect of R0. So now you can put that R0 back. You will get a more accurate expression, but will it make too much of a difference? Yeah. Right. So yeah. So now the question is, if I put back if I put back R0, essentially I am getting what is the purpose of this stuff? The purpose of this stuff is to essentially figure out what is the effective resistance. If I know the effective resistance, then I know the effective current, right? So now if I put back R0 here, so I'll get 1 over GM times R0. That's effectively, 1 over GM, right? So this current now, instead of GMVI by 2, the expression will be GMVI by 1 plus GM times 1 over GM parallel R0, right? So granted that this will not be GMVI by 2, it is slightly less than GMVI by 2, right? So that you are incurring an error there. I agree. But the question is that error significant? Now see that whenever the current flows and comes to this node Vx, the stuff that we are more interested in is what is the current that is flowing here, right? Not particularly. So if there is error here, if there is an error in the current that is flowing into Vx, there will be an error that we calculate by for the current that is going into R0. But the question is that error significant? Again, if the error is not significant when we are calculating the error here, that will not be significant there. The stuff that you have to be careful about is all these currents are getting added up, but for when we are doing the division at this node, right? So these errors are not significant when you are adding up currents. If there is subtraction of current, where two significant parts are getting cancelled off, then you cannot make that approximation. Okay. So yeah, so it's sometimes equivalent to saying, let's say I have two numbers, one is 1,000,001, another number is 1,000,000. When I subtract them, I get 1, right? So I cannot neglect that 1 when I am subtracting. But if I say I'm doing 1,000,001 plus 1,000,002, then effectively it's 2,000,000, right? It doesn't really matter 2,000,003 or something. So it's that analogy. Okay. Okay, fine. So so this is this. So if we have so now the current that is flowing through I1 when only input is applied at the gate of M1 is this. What will be the current that will flow when the input is applied only at the gate of M2? This is VB plus VI. Now we are interested in only small signals, so you can neglect VB. What will be the current now through R0? It will be exactly the same. There's no difference between the cases where input is applied at M1 or M2 with regards to this current. So this current will again be, let's say I call it I2. This will be GMVI by 2, 1 plus GMR0. Now, if I use superposition, then what will be the current through RL? So basically, I'm putting back two cases. I'm putting back the input at M1 and M2. So using superposition, IRL, or let's do I0, that is the current through I0. IR0 will be I1 plus I2, which will be GMVI by 1 plus GMR0. And again, I mean, basically I can, in 1 plus GMR0, I can neglect 1. So this effectively becomes VI by R0. So this current flows through RL, right? So this current flows through RL and develops a voltage. This is in case of input applied at both the gates simultaneously. So this current essentially is V0 over R0, and this is RL. So this voltage, VI over R0. This voltage, that is VOCM, that is the common mode voltage, is VI by R0 times RL, negative of that. Okay, so this becomes the expression for common mode voltage, rather times VI. So common mode gain, that is ACM, is VOCM by the average of the two inputs. The average of the two inputs is VI, becomes minus RL. Okay, so as you can see that if R0 goes to infinity, from this expression also we get the output common mode gain to be 0, which we also got using intuition in the previous case. Okay, any questions? So is it, I mean, is it curious? Do you see, I mean, this expression is very simple, right? VI over R0. We did all sorts of things and we came up with VI over R0. Is there a way we could have come up with VI over R0 directly? The current through R0 is VI over R0. We did a superposition, applied this side, that side, canceled some stuff, added some stuff, and ended up with VI by R0. Do you think, is there a simpler way of arriving at that expression? This is the total, which means input has been applied on both sides simultaneously. Right, exactly, right? So approximately the voltage at the center is the average of the two guys, two inputs. I'm saying approximately because that expression of the voltage at the center is exactly equal to was based on the fact that R0 is infinity. Right? In cases of R0, it will not be exactly average, but it will be approximately average. So if it is approximately average, then what will be the voltage at Vx at this node? Yeah. So if this is Vi, this current is Vi by R. Right? So often you see that this is also done in with regards to a symmetry, because differential amplifier with regards to many things is very symmetrical or anti-symmetrical depending upon what type of inputs you apply. Let's say I only consider, no, let me consider the full one. So if I neglect channel length modulation for M1 and M2, neglecting channel length modulation for M1 and M2 effectively means that whatever happens at the drain does not affect at the source, right? Neglecting channel length modulation means that the voltage excursion as the drain does not affect the source, right? So you have infinite isolation between drain and source. So channel length modulation effectively means that you can disregard whatever is connected at the drain. So if that is the case, if I can disregard whatever is connected at the drain, if I am neglecting channel length modulation, then from the perspective of this, if I draw a line there and I say that I only look whatever is happening in the bottom part of the line, then everything is symmetric, right? Since everything is symmetric, incremental current through M1 will be exactly equal to the incremental current of M2, and whatever voltage I have here, Vx, then I should be able to analyze by splitting the circuit into two halves and only analyzing one half, right? So how do I split a circuit into two halves? M1 and M2 is easy to see. I can basically split it down the middle. But what do I do with the resistance? Yeah, right. So I can, if I have to shift the resistance between two sides, all I can say is that this becomes 2R0. This becomes 2R0. So if I split it down the middle, then is there a current incremental or steady state that will flow through this wire? No, right? Because now there is no need for the current to flow from one branch to another, because both the branches are identical, all the voltages will be identical. So which means that I can remove this. I can remove this branch altogether without affecting the common mode response of the circuit. Right? Note that this is only possible because we have applied identical inputs for this input condition. This is not possible generic in a generalized sense. So if this is the case, then it's quite simple. This current will be VI by 2R0, right? So since this current will be VI by 2R0, what will be this voltage? This will be VI by 2R0 times RL. I think I missed a factor of 2 somewhere earlier. So let me just look at it once. Hold on. So this becomes, this is GMP by 2. This is fine.
Current to RL should be VI by 2R0.
Right. So where did I miss that factor of 2?
In this figure.
Correct. Yes. Yes. Thank you. Okay. Yeah. So this voltage, I mean, in the actual sense, this voltage, this current would have been VI by R0. So it would have split equally between two halves. So I should get VI by 2R0 on the other side, right? Yeah. Fine. So now it adds up. So now you see that in these two cases, you have essentially identical response, but it looks like in this case, we didn't have to do any math, right? We basically understood from our previous analysis and from some sort of circuit intuition that these blocks will be identical, so we could split them down the middle. Okay. Any questions? Okay, fine. So now another crucial trick that we sometimes can use is just like we can use this. Right? This is called a half circuit analysis because we are only looking at one part of the circuit to find out what is happening to the total circuit. So can we use the half circuit analysis for the differential mode also, right? So we did the differential mode using full blown, but let's see if we can use the half circuit analysis for a differential circuit also, or differential mode also. VB plus VI by 2, this would be VB minus Vi by 2. So now in case of a differential input, essentially we are trying to figure out, do we have an axis of symmetry or anti-symmetry? So in this case, there is indeed, again, because again, if I try to figure out the axis of symmetry, and let's assume it's the same as in case of a common mode, then we will be interested to find out what is this voltage Vx. Now this voltage Vx again is approximately equal to the average of two incremental inputs. If that is the case, this voltage Vx will be approximately 0. But in this case, you can do the brute force analysis also to find out that Vx will not be approximately 0, it will be exactly 0, because ultimately the voltage directions at M1 and M2 are opposite, which means the current that will come from M1 and M2 will also be in opposite direction and equal in sign, or and equal in magnitude and opposite in sign, right? So which essentially means that whatever current comes to M1, the impedance that is both sides are seeing are same, which means it will develop some positive voltage at this node Vx. And if and the similar analysis when you do with M2, it will develop the negative voltage at the node Vx, and they will cancel out, right? So without doing any analysis, you will be able to figure out that this Vx will be approximately equal to 0. If that is the case, then I don't have to do much analysis. Then I can simply say that this R0 is irrelevant because no current flows through R0 anyways, and this voltage is actually 0, which means I can only again now look at the right half of the circuit, right? The right half of the circuit will give me a current of Gm times Vi by 2 going up. So this will be Gm times Vi by 2 going up, and this goes into this current, and this one goes into this resistance RL and produces a voltage of Gm Vi by 2 RL plus, not minus, plus. Okay, so the ratio, so now this becomes a differential gain. So the so the ratio of this with respect to the common mode gain is essentially our common mode rejection ratio. Okay, make sense? And ideally, we would like to have an infinite common mode rejection ratio, but in principle, infinity is not possible. But in this case, what is the common mode rejection ratio? If I take a ratio of this and that, you see that approximately this is Gm R0, right? Which Gm and which R0? Gm of M1 and M2, and R0 of the tail transistor, that is M0. Okay, so in order to improve common mode rejection ratio, you need to either increase the Gm of M1 and M2 or the output resistance of input. Okay, fine. Any questions? Okay. So now let's discuss something which is related to DFAM, but which has been bothering us right from the days of common source amplifier, and that is the fact that we are kind of limited by the maximum gain that we can achieve is kind of limited by the power supply, right? Because if you have to increase gain, you have to either increase Gm by increasing current, or you have to increase RL. If you have to increase RL, then you have a lot of quiescent drop. If you have quiescent drop, then your transistor goes out of saturation, which means there is a maximum amount of RL that you can have for a certain amount of current or certain amount of Gm, which means that Gm times RL, there is a maxima, and that maxima is determined by the amount of headroom you have, rather amount of VDD that you have, right? That you have seen during your simulation assignment also. So in a nutshell, this is the problem. So let's say this is VB plus VI. It's a common source amplifier. Now, whatever is happening with the common source amplifier, this problem will still be the same in case of a differential amplifier. So the issue is, if I have to, our gain is, mod of gain is Gm times RL, which is exactly the same, or not exactly, by factor of 2 is different, but it is kind of same in case of a differential amplifier also. So now if I have to increase the gain, I have to increase RL. If I increase RL, this for a finite VDD, right? So since this drop is going to increase, the quiescent drop is going to increase. Since the quiescent drop is going to increase, transistor M1 will tend to go into linear, right? So the main problem here essentially is the gain is so let me find out the quiescent drop also. This quiescent drop essentially is I naught times RL. Let me call this IDS. Let's see. It's IDS times RL, right? And IDS again is a function of GM, or GM is a function of IDS, which means that the problem is gain is dependent on quiescent voltage drop across RL. Okay. To increase gain, ideally, I would like to make RL to be very high. But if I make RL to be very high, the quiescent drop increases and throws my transistor out of saturation. So that's a big problem. So what is the, now a solution should exist because what is the effective impedance looking in here if I include the channel length modulation? Yeah, right. So this is RL parallel R1, let's say, where R1 is the impedance of incremental impedance of M1. Now, in principle, this R1 can be much higher than RL, right? Ideally, if I neglect channel length modulation, it's infinity, right? It cannot be infinity, but can be fairly high. But the important thing is that we see that this R1 is not dependent on the quiescent voltage drop, as long as the transistor is in saturation. If the transistor is in saturation by 100 millivolt or 200 millivolt or 1 volt, doesn't really matter. R1 doesn't change too much, right? So we see that a solution exists if we can replace RL with another transistor whose drain is connected there, right? So what I'm essentially saying is that this resistance here is R1. This is more or less independent of VDS if M1 is in saturation, right? So, but the impedance looking here, which is RL, this RL is independent of VDS, but the drop across RL is not. Right, the drop across RL is dependent on the quiescent current, right? So in this case, in the first case, in the M1 case, it is independent of VDS, which implies that it is of the quiescent current. Okay, since this is independent of quiescent current, I don't have to bother about the drop across the transistor. But in case of a resistor, I have to bother about the drop across it, because the drop across the resistance essentially will determine whether M1 will be in saturation or not. But let's assume we have another device. Let's assume we have another device whose impedance, when I am looking from this node, let's say something is connected here, and I am looking for the impedance looking up into that node. This is also equal to of the order of R1, right? Let's say this is R2. Which means I'm looking at the drain of the transistor, looking up there. Then there is a chance that whatever argument that I am applying for M1 will be applied for the device that is connected on the top. Do you agree with that argument? Or do you want me to explain it further? Let me anyway explain it further. So what is the main issue? The main issue is the gain is dependent on the voltage drop. The voltage drop is dependent on the current, quiescent current, right? So which means that the gain is dependent on the quiescent current. I want to make the gain independent of the voltage drop. In other words, I want to make the gain independent of or less dependent on the quiescent current. And it looks like the transistor in the bottom has an output resistance which is kind of independent of the quiescent current. To some extent, it's dependent, but I mean, at least the voltage drop across it is not particularly related to the output resistance, right? If the voltage drop is not related to the output resistance, then there is a chance that if such a similar transistor is connected to the top, then I should have similar properties. That is, the voltage drop across it, it will not be dependent on, will not be directly related to the output resistance of that device, right? You seem lost. So what's bothering you?
The whole RL is replaced by another.
Yeah, I have to replace RL with something which has similar properties as this M1. Do you see the problem, or the problem doesn't exist?
So we want that the drop across that device should be less.
Right.
But if we were looking from bottom, then it should be of the order of the R1.
Right. So yeah, so that's actually very well said. So whatever you're saying is the drop so let's assume I have a 500 millivolt drop across VDS across M1, and for that, let's assume we have like 1 milliamp of current, right? But if I have to get a 500 millivolt of drop for a 1 milliamp of current, what is the if I have to replace an RL there in case of a common source amplifier, so what is the value of RL that I'm looking at? 500 millivolt drop, 1 milliamp of current. What is the 500 ohms, right? So essentially, I have to put a physical 500 ohms resistance there, right? So now, if I have to increase the 500 ohms resistance, let's say 1 kilo ohm or 2 kilo ohm or 10 kilo, then I am naturally increasing the voltage drop across the resistance by factors of 2, 10, 100, and so on, which means that it's not sustainable with the finite voltage supply. But let's say I want to increase the R1. I want to increase R1. What can I do? What is the easiest way to increase R1? Yeah, what changes R1? No, for a particular transistor, you have to increase the output impedance. What is the easiest first thing that you should try? L should be high, right? And if you don't want to change GM, you also increase W, so that W by L remains constant. So I increase both RW and L by a factor of, let's say, 10. Then R1 increases by a factor of 10, right? And does anything change to the quiescent current? No. Quiescent current remains exactly the same, but does anything change to the VDS, quiescent VDS? Current remains same. Transistor is in saturation. I didn't change the resistance on the top, which means quiescent VDS remains the same. So there is a way of keeping the VDS constant and increasing the output resistance, right? But if you put an RL on top, you don't have any such handle. If you have to increase RL, you have to suffer that quiescent voltage drop. So I want to put something there to replace RL so that I don't have to suffer that problem. Okay, now it's clear. Okay. So now, which means naturally it's not a resistor, it has to be a transistor. So let's say I put a transistor here. This is the only transistor that we know, and let's say it's biased properly and all. So let's say this is VB2. So what is the resistance looking up into this terminal? It's 1 by GM, right? So this is definitely not a very high impedance. So simply putting a transistor will not suffice, because we need to put a transistor whose drain is connected to that node. In this case, the source is connected to the node. Now, what determines whether a node is source or drain? Voltage, right? Quiescent voltage. So the low voltage stuff has to be, in this case, the low voltage stuff has to be the source. But we are looking for a device whose drain is connected to the node, which means we are looking for a device, in other words, whose low voltage stuff is the drain. That definitely NMOS transistor is not such a device. Okay, so we are looking for a transistor whose okay. So in case of an NMOS, it's not possible, but I'm sure you have done this in your UG curriculum. We have another device called PMOS, which does exactly this, right? So in case of a PMOS, so let's draw the NMOS and the PMOS and do the comparison. So again, this is drain, this is source, this is gate. This current is IDS. So we have another device. It's a complementary device whose symbols, there are two types of symbols which are used, but let's use the symmetric symbol first with a bubble here. So in this case, we call this source drain gate and this current ISD. So the expression of IDS and ISD are exactly, I mean, almost similar with a slight variation in sign. So in this case, the current flows from drain to source in case of an NMOS, right? So this IDS flows from, even before going there, let me use some definition. So in case of an NMOS, we see that the higher terminal, higher voltage is drain and lower voltage terminal is source. In case of a PMOS, the higher voltage terminal is source and the lower voltage terminal is drain. Okay. So in case of an NMOS, the current, I mean, the transistor turns on when, so on when VG minus VS is greater than some threshold voltage, VTN. In case of a PMOS, it is on when VS minus VG is greater than some threshold voltage, right? It's some voltage. We'll see why I call it mod later on, but let's stick with mod for the time being. So threshold voltage of a PMOS transistor. Okay. So and the current equation, naturally, if everything is symmetric, just that their polarities are different, the current equation in the case of an NMOS in saturation becomes is half mu n Cox W over L VGS minus VTHN whole squared times 1 plus lambda VDS. In case of a PMOS, it's the terminals are flipped. So essentially, this, whatever is drain becomes source, whatever is source becomes drain. So this becomes ISD is equal to half mu P Cox W over L VSG minus mod VTP whole squared times 1 plus lambda VSD. Okay. And in case of a device in linear, this is in saturation, so this is in sat. And in case of a linear device, this becomes half mu n, sorry, not half, right? Mu n Cox VGS minus VTHN times VDS minus half VDS squared. So in case of a PMOS, this becomes exactly similar, but wherever you have VSG, it will VGS, it will become VSG. VSD minus half VSD square. So this is as far as the algebra part of NMOS and PMOS is concerned. We'll move to the device dimensions or how the device looks like, the cross section of a device shortly. But I wanted you to understand that this is a complementary device. This is not a different type of, different configuration of NMOS. It's a different device whose fundamentally it's quiescent wise, it has a difference that even though the currents looks the same, the fundamental difference is that a higher voltage terminal is the source and the lower is drain. Another difference is that in case of an NMOS, the device turns on when the gate goes above source. In case of a PMOS, the device turns on when the gate goes below source. Right? So essentially we are looking for, in case of an NMOS, we are looking for a positive VGS, right? In case of an PMOS, we are looking for a positive VSG. Okay. So in many books in the literature, you will see that because sometimes we want to keep the device equations and everything same. So we also tend to use the same expression, that is VGS, in case of PMOS also. In that case, what essentially happens is that this VT term becomes negative, because we want, with respect, if the on condition is positive with respect to VSG, positive voltage, it will be a negative voltage with respect to VGS. So in the literature, especially in the device physics literature, everything is expressed with respect to VGS. So we tend to call threshold voltage negative for a PMOS. Okay, enhancement type PMOS rather, we tend to call it negative. But for when you are doing a circuit design course, we are particularly not bothered about which type of equations you need to keep. We are only bothered about how easily we can interpret the equations and interpret the functionality of a device. So we tend to then say that we forget about this negative things, difficult to memorize all those things. So we'll try to make sure that the device equations and everything looks symmetrical. Whatever we have learned with an NMOS should be valid for a PMOS also, because equations are identical, IV characteristics are identical. Maybe the values will be different, but as far as the small signal model is concerned, as far as the device properties are concerned, they should be identical if we just remember 2 or 3 simple things. What are the simple things? One is quiescent wise, there is a difference. Source has to be a higher terminal. Between source and the drain, the source has to be a higher voltage in case of a PMOS. The device turns on when the VSG becomes positive over certain threshold voltage, and that threshold voltage is mod of VTHP, right? Because again, we are trying to differentiate between the literature in device physics and in circuits. So we will use this mod of VTHP, and mod of VTHP is always positive. So essentially, we don't have to bother about whether you are taking VGS or minus VTHP. This is the convention that we will stick to. Okay. Okay, so now, so let me quickly go through the cross section of the device just for the sake of clarity. So in case of an NMOS, you have a P well, and you dig 2 trenches of N+, and you have oxide here and a metal on top. So this becomes metal. In today's technology is polysilicon. And you identify one terminal as drain, other as source. And the only way you know that, whichever is the higher voltage, becomes the drain and the source. And in order to turn the device on, you'll have to apply a positive voltage between the gate and the source. This is a NMOS device. In case of a PMOS device, since it's a complementary device, so everything will be opposite. So here you have P plus, so here you should have P minus, here you should have N minus. Here you have N plus, so here you should have P plus. This remains the gate. And if I say this is a lower terminal voltage, so let's say call it VD. This is drain. This is source. In order to turn the transistor on, you have to apply a voltage between gate and source. But between gate and source, which terminal has to be the lower? Which terminal has to be the higher? Source has to be higher. So essentially, you'll have to put a battery like this. So in this case, the battery was like this. Okay. So and when device turns on, in case of an NMOS, you have inversion, and inversion creates mobile electrons in the channel. In case of a PMOS, it will create holes in the channel. Okay. In case of an NMOS, in the channel, the electric field, the vertical electric field was going from top to bottom because gate is at a higher voltage. In case of a PMOS, the electric field goes from bottom to top, right? So it should not cross over the channel ideally. Okay. And similarly, the horizontal electric field in case of an NMOS goes from drain to source. Right. So this is the horizontal electric field. In case of a PMOS, the horizontal electric field goes from source to drain. Okay. So again, operation wise, it's, I mean, if I choose to neglect the device physics aspect of the device, and we only deal with the IV characteristics of the device, IV characteristics of a PMOS will be exactly same as the IV characteristics of an NMOS, just that the terminals will be flipped. Wherever you are plotting VDS, you will be plotting VSD. Wherever you are plotting VGS, you will be plotting with respect to VLD. Okay, everything else remains the same. Another critical thing that you should be mindful of is sometimes what we tend to miss initially is what is the condition of saturation. In case of a PMOS, in case of an NMOS, what is the saturation condition? So VDS has to be VDS has to be greater than equal to VGS minus threshold voltage. Or I can forget about the source because source is common. Right. So in other words, what it is saying, there is a minima for the in this case, there is a minima for the drain voltage. You can push the drain voltage to a certain level. I mean, you can start off with a very high voltage and then keep on pushing it down till it reaches linear. So there is a minima condition associated with the saturation region for an NMOS transistor. But what is the similar thing for a PMOS transistor? So in case of a PMOS, in case of a PMOS transistor, so now what is why do we have this condition? We have this condition because ultimately this is decided by the pinch off, right? So in case of a device, we saw that long back, we saw that in order to ensure that there is pinch off at the drain channel junction, we needed this condition. So what is the equivalent condition of pinch off in case of a PMOS? In the case of a PMOS, the equivalent condition of pinch off is if I look from the device perspective, which side in this device, which side will the pinch off occur, on towards the left or towards the right? Towards the drain side, right? So essentially, your charge profile should look like this, right? Towards the source, it has a lot of charges. It's depleted towards the drain side. Okay. So if that's the case, so if there is a minima condition with respect to, in case of NMOS, if there is a minima condition with respect to VD and everything is complementary in case of a PMOS, do you think you will have a minima condition of VD or will have a maxima condition of VD? We'll have a maxima because everything is flipped. Okay, so which essentially means that so in plain English, in case of an NMOS, we are saying that there is the minimum VD. So to keep transistor in saturation. In case of a PMOS, we should say that there is a max VD. Okay, and as it turns out, the requirement in this case is the drain voltage. Just like in case of an NMOS, you can start off with a drain voltage and can reduce it. In case of a PMOS, you can start off with a low drain voltage and keep on increasing. And there will be a maxima that you can hit before which the transistor goes out of saturation. And that condition is VD should be less than equal to the gate voltage plus the threshold voltage. Okay, so in other words, if I take an example, so let's say this, in case of an NMOS, this is 1 volt, or let's say this is 2 volt, this voltage is 2 volt, and threshold voltage, let's say, is 1 volt. So what is the minima of the drain voltage? 1 volt, right? So essentially, there is a the drain voltage can go 1 volt below the gate voltage. So this is minima is 1 volt. In case of a PMOS transistor, if the gate is stuck at 2 volt, what is the maxima of VD? 3 volt, right? So VD can go up to 3 volt. This can go up to 3 volt. Okay, so in case of a NMOS transistor, let's say the gate is at 2 volt and the drain is at 1.5 volt in saturation. In NMOS transistor, gate is at 2 volt, drain is at 1.5 volt. It's in saturation? Yes. In case of a PMOS transistor, the gate is at 2 volt, drain is at 1.5 volt. Or let's say drain is at 2.5 volt. It's in saturation? Yes, right? Because this can go higher than this. Right. So this is a slight mental model tweak you'll have to accommodate in your mind. So essentially everything that we have done in case of a NMOS is valid in case of a PMOS also. So that there are certain conditions you have to ensure that they are taken care of. Okay. So just to tie the loose ends up, if we are using these, if the notation in case of an NMOS has an arrow, the notation in case of a PMOS also should have an arrow. And again, the arrow is typically, it marks wherever the source is, right? So in case of a PMOS, that's why the alternate symbol is this. Okay, so arrow is connected at the source, and the direction of the arrow points to the direction of the quiescent current. Okay. Okay, fine. So if everything looks same, then it's not a surprise that our incremental picture also should look the same for both devices. Okay. So in case of an NMOS, the incremental picture was this. I'm not drawing the capacitances. This current source was GM times VGS. In case of a PMOS, I should also have something similar. So in case of just like in case of a NMOS, in case of an NMOS, we had flipped the directions, right? The source was on the top. So if I do that, so if I say that this is VS, this is VD. So this current should be GM times VGS. So what should be the direction of the current? Everything is same, but with a slight difference of the signs, right? So I'm keeping this to be GM times VGS. So what should be the direction of the current? Pointing up, right? Yeah. And this is R naught again, right? Now the natural question is, what is GM? Let me call this GMN. This is GMP. So in this case, GMN was the definition of GMN was dou ID dou VGS, which in this case was mu n Cox W over L VGS minus VTHN, right? So similarly, in case of a GMP, the definition will be dou ISD dou VSG. Okay, so this will be. So if I do this, what should I get? I should get mu P Cox W by L, then VSG minus mod of VTHP. Okay. Questions?
Just have doubts
Uh-huh.
direction.
Oh, in this case? Okay, okay. So do you think it should be from top to bottom? Okay, so why do you think it should be from top to bottom? PMOS current flows from source to drain with regards to the quiescent current, right? So let's argue in this way. So if PMOS and NMOS are supposed to be similar, then if I increase the gate voltage of the NMOS, do you expect the current to be drawn out of incremental current to be flowing into the device or out of the device? I'm increasing gate voltage. So let me ask you in this way, which will probably be more comfortable. If I increase gate voltage, do you expect the drain voltage to increase or decrease? Decrease, right? So in case of a PMOS also, you want the same thing. We expect the same thing because essentially it's the same device. I mean, it's complementary device, but essentially having same structure. Which means if I increase gate voltage, I would expect the drain to reduce, right? So in this case, see, does this conform with that? If I increase gate, I'm pulling current out of drain. Right? So you are expecting the drain voltage to reduce. The same thing is happening in this case also. Right? So again, so we can come at it from first principles also. It's not as if you have to argue in this manner. The first principle argument is this. What is GMP? GMP is, by the very definition that we have used, GMP is dou IDS, dou ISD, dou VSG. Okay. So if I retain this, then I will have, instead of this current source being expressed as GMP times VGS, I should express this in terms of GMP times VSG and then flip it down. Right? Your argument of current flows from source to drain is correct. But if I have to use that argument in case of a incremental circuit also, then the definition should be, this should be GMP times VSG, because in the total expression also it was VSG minus VTP whole square. So this has to be GMP times VSG, and then I flip it down. It goes from source to drain. But since I want an equivalence of those two, because we deal with incremental circuits a lot, we don't, effectively these two incremental circuits are identical. Right? Just that I have flipped it everything and flipped the directions. Here also is GMVGS, here also is GMVGS, here also the current flows from drain to source, here also the current flows from drain to source. So if I give you an incremental circuit, there is no way you can tell whether this comes from a PMOS or NMOS. Because everything is identical. You will need the total circuit to understand, quiescent circuit to understand whether it's a PMOS or NMOS. Okay? Okay. So if this is the case, then things become kind of simpler, because now we have a device which we can connect in case of an NMOS transistor, right? In case of a common source amplifier, we were looking for a device to replace this resistor. We are looking for a device to replace this resistor whose drain is connected here, right? This should be looking into a drain. And this has to be, by the very fact that the current is flowing from top to bottom, this has to be the low voltage terminal. So in case of a PMOS, it was not possible. In case of an NMOS, it was not possible, but we have another device, which is a PMOS transistor, for which it will be possible. Okay. So which means that I can essentially say that let's connect a PMOS device here. NMOS, we already know. If I simply connect these two, this is VDD, and let's say this is biased at VBP, right? And let's say this is V0. So if this is the case, let's take some examples. Let's say VB equal to 2 volt. And let's further take that threshold voltage of NMOS is 1 volt and threshold voltage of mod of threshold voltage of PMOS is 1 volt. Because ideally, threshold voltage is defined with respect to VGS. We are doing everything with respect to VSG in case of a PMOS. Let's assume that the current, this current I0 is 1 milliamp. Let's further assume that this current is 1 milliamp. Okay. And let's further assume that this voltage V0 is equal to, I don't know, maybe 2 volt. How, I don't know. We'll have to see later. But let's assume that there is some additional circuit somewhere that has set this voltage to 2 volt. Why am I saying some additional circuit somewhere? What, can I definitely say what this voltage will be? So let's say, forget about this PMOS. If I had a current source here, connected here, can we definitely identify what the voltage will be? How? Current will be equal, but what will that voltage be then? Because if I neglect channel modulation for in case of a NMOS, there is a range of voltage for which the current will be valid, right? Because both are current sources. And we saw that that is not particularly a good way of biasing anyways, because transistors can go out of saturation. So the point that I'm trying to make is that if this is the current source, then there is no way you can tell what the voltage will be. Now you can say that channel modulation equation has a VDS term. I'll take that out and find out whatever it is. But again, that is not a particularly good way of going about it, because you are relying on second order effects to find out a voltage, which is not practically a very good design. So let's assume that there is some feedback network somewhere which is setting this voltage. Just like negative feedback we saw sets voltages at different nodes. There is a feedback network which sets this at 2 volt. So now, why am I drawing the analogy between the current source and this PMOS? Because I did so in case of an NMOS, for example, if the VGS is fixed, this behaves like a current source. Not a very good current source, but still it is a current source. In case of an NMOS with a fixed VGS, is a current source. In saturation, obviously. In saturation, an NMOS transistor with a fixed VGS is a current source. So similarly, in saturation, a PMOS transistor with a fixed VSG will also be a current source. Right? So this guy essentially is a current source. What is the, right? So if this is the current source, the behavior of this circuit will be exactly the same if there was a current source on the top. Right? Okay. So now tell me what is the maximum, rather tell me what is the condition on the gate voltage of this PMOS to keep the PMOS transistor in saturation. This is M2. Firstly, let's see whether it's a maximum or a minimum we're looking at. So if VBP goes high, and let's forget about let's assume the transistor is on, we don't have to worry about VDD. So if VBP goes high, do you think that M2 is going more into saturation or more into linear? More into saturation, right? Because ultimately we want, or not we want, essentially the condition of linear decay is this voltage goes higher than VVP by a threshold voltage. That is the maximum we can lift this voltage. So in other words, if the difference between these two increases with regards to this V naught becomes higher, then the transistor is going into linear. In this case, the opposite is happening if I keep on increasing VVP. Right, I am going away from linear region. So which means that the condition of linearity will be valid when VVP goes low. Right? So if VVP goes low, how low can it go? If the threshold voltage is 1 volt, minimum VVP will be 1 volt. Right? So 1 volt below, one threshold voltage below the drain voltage, so minimum VVP is 1 volt. Fine. So, so as long as VVP is greater than 1 volt, we are good. So what is the constraint on VDD? I need the transistor to be at least on. Let's say by similar overdrive. In this case, let's assume 1 volt. I want a 1 volt overdrive once in case of a M2 also. So what will be the constraint on VDD? Threshold voltage is 1 volt, so 1 plus 1 and 1 volt of overdrive, let's say. So greater than equal to 3 volt. Right? So VDD has to be greater than equal to 3 volt. This is assuming the overdrive of 1 volt. Okay. So now you see that this common source amplifier equivalent is behaving like almost like an ideal common source amplifier with a PMOS device with a fairly low supply voltage. Right? With 3 volt, you are getting the output impedance which you would have gotten with in case of a current source. And as long as you can keep, and let's say you did this analysis and you found that your PDS is rather your gain is not good. We have not yet calculated gain. We'll do that next. Let's assume the gain is not good. You want to increase the gain, then what should you do?
R2.
Yes, then how are you going to increase R2? Yes, so how? So let's say I want to increase the output resistance of this. I want to increase the R2 output resistance of the PMOS. How do you increase the output resistance of an NMOS, for example? Right? So what should you do for PMOS? Again, same, increase the length, right? So if I have to double the output resistance, I have to increase L by factor of 2, or I don't want to change current, so I have to increase W also by factor of 2. So I can simply increase the W and L by factor of 2 here, same W and L, W and L by factor of 2 here, W and L by factor of 2 here. So I will be effectively increasing the output impedance by factor of 2. I will not be changing current. Will I be changing? I mean, that will not change current, and will it have any effect on VDD or linearity stuff? No, nothing, right? So both the transistors will be on linear. So you see that you can almost arbitrarily keep on increasing the output resistance with the same voltage supply.
In that case, the output resistance of the lower transistor will also increase.
Both will increase. Yeah, I couldn't hear your question.
It will come in parallel with.
Right. So we'll do that. We'll do that next. But essentially, what I'm trying to tell you is that from this picture, there is a way of increasing output resistance or increasing. The output resistance is not dependent on the quiescent drops across the transistors. In this case, it is not. In this case, for now, it's not. You can effectively keep on arbitrarily increasing output resistance having the same VSD, which was not possible in case of a passive RL. Okay. Okay. So now let's proceed and replace both the transistors with the incremental equivalents. In case of a NMOS, it's quite simple. We have done it like infinite times. So in case of a PMOS, this is something new. So in case of a PMOS, we'll use this. We'll use the same thing. So the drain is wherever the drain VD is the drain. So this was anyways the drain. So I can basically use the same structure verbatim. this becomes GM VGS. In case of a NMOS, we had the voltage source connected here. In case of a PMOS, what should I connect at the gate in the incremental model? I have a constant voltage source connected at the gate. So in the incremental model, what should the gate be? Ground. What should the source be? Ground. So essentially this becomes must be not. Okay, so what will be VGSP? 0. So this goes off. So what is V naught over Vi? Minus GMN, it's GMN times R1 parallel. Okay, so you can have, now you see that R1 and R2, I mean, output resistance is not limited by the RL, which was actually the case earlier. In this case, your output resistance is output resistance of 2 transistors in saturation, which again is kind of independent of the quiescent voltage drop across VDS. Okay, so it's basically you get another additional handle to increase the gain arbitrarily almost. You get another handle to increase the gain arbitrarily without thinking too much about whether the transistor will go out of saturation because drop across RL and so on. Okay, any questions? So now the natural thing to do is to say that we have done all this everything with NMOS, which essentially means that I can do everything with PMOS also, right? So I'll show you one quick example, then you can maybe post an assignment, you can have it for practice. So in case of an NMOS, let's say I go back to the single transistor, 1 resistor common source amplifier. So since NMOS and PMOS are essentially brothers, right? So we can have the same circuits, I mean same functional circuits with both NMOS and PMOS. So what is the only difference in case of wherever I have NMOS, I have to replace it with PMOS and then see how the circuit shapes up and then bias appropriately, right? So we have this is the NMOS common source amplifier. Let's make a PMOS common source amplifier. So transistor M1 is there. So I'll put in place of the transistor, I will put another PMOS device. Let's use this bubble because we don't yet know which is the source, which is the drain. So now tell me which side would you like to be the source, which side would you like to be the drain? Then we can proceed accordingly. Bottom you want to be the source? Okay, so let's say bottom is the source. Now source is the higher terminal, higher voltage or the lower voltage in terms of quiescent, higher voltage, right? So in case of a common source amplifier, in case of an NMOS common source amplifier, the source is grounded, right? Incrementally also and in the quiescent state also, right? So now you tell me the current in the NMOS transistor flows from drain to source, from top to bottom, IDS. In case of a PMOS common source amplifier, the quiescent current should flow from source to drain. So it should go like this. Right? So this is kind of unwieldy in the sense that we always mostly associate currents, quiescent currents at least, to flow from top to bottom, like gravity, water falling and all. So what people generally do say is that doesn't look good, we'll flip it. Right? So we'll flip it and we'll put the source on top. So the current still, quiescent current still flows from top to bottom. Okay. So now, where is the RL connected? Drain or source? Drain. So RL here will also be connected at the drain. Now, what should I connect to source and what should I connect here? Because the current is flowing from top to bottom and I have to connect VDD and zero, ground. So where should I connect VDD and where should I connect ground? Right. So naturally VDD has to go to the top because current flows from VDD and goes into ground. Since the current is flowing from source, in this case, it has to be VDD. This has to be ground. And we'll have to obviously apply a voltage, at this node. And if I have to draw the equivalence, the voltage is applied between the gate and the source in case of a NMOS transistor. A positive voltage is applied between the gate and the source of an NMOS transistor. A positive voltage should be applied between the source and the gate in the PMOS transistor, right? So it should have this. Okay, this has to be VSG. And now you have to apply the voltage also, incremental voltage also, just like you had put it in series in this case, I can apply a voltage in series in this case also. Okay, so this is an exact equivalent, but I mean, we know the problems with this type of biasing, right? When you cannot put them in series and those and so on and so forth. So what you did in case of an NMOS transistor will also be valid in case of PMOS transistor. You put a voltage divider, put this, and put this. Because in an incremental model, one might argue that I can apply this incremental input to VDD also. Fine, you can apply, but really doesn't matter because the incremental model is the input is coming essentially from a previous stage, right? So you can anyway AC coupling, so you can essentially do this. Okay, fine. We'll stop here. We'll start from the next class.